Okay, so here's where we left off. We have taken the curl of this equation, okay, and so we take the curl of the left and the right hand side, and then we can rearrange this part, can bring the time derivative out, the curl in, and we get this, okay, and now this the curl of the magnetic field is given by this this one of Maxwell's equations, and so this is now equal to minus epsilon naught mu naught times the second time derivative of the electric field. Okay. Now remember, you may recall some identities that have to do with the del operator. Okay. So this expression can be rewritten like this, and I'm not going to prove this, but I may ask you to prove this. Okay, now this is just an identity, and but the divergence of the electric field is given right here in the vacuum where by 0. So this right hand side 0, so this goes to 0. Okay, and this is basically the Laplace operator, which we traditionally write with this nabla symbol, which looks a lot like a delta, like that. So and so in the end, we're left with an expression that the Laplacian minus second time derivative of the electric field is equal to 0. Okay, so let's highlight that. All right. So we have the Laplace operator is just a second order spatial derivative, and we have a second order time derivative. So if we want to evaluate this, we actually have to consider an actual wave. So we have to consider the form of a wave and actually take the second spatial and time derivatives. Okay, so let's do that now. Oops. Let me pause. Okay, so for a wave, a wave of time period t and space period, that is wavelength, equal to lambda, which is also equal to the speed of the wave times t times the period along the x direction. Okay, we're considering a wave that's moving along the x direction. Then in that case, the electric field, remember this is an electromagnetic wave, so it's got a sort of a periodic sinusoidal form. So we've got a cosine, and we've got this factor, this phase factor, which is the depends on the time. Remember, the electromagnetic wave is periodic in both time and space. So there's the time part. Here's the spatial part. Okay, it's the time divided by the period, and the spatial coordinate divided by the spatial period, or the wavelength. Okay, and so if we take the first derivative of this, let's just do the simple calculus.